to be calculated based on the our mean position. So mean position, from that mean position, this is the final elongation, this is the final shortening. Now, once the ball is moving upward, let us say at that situation, the spring is maximum compressed by this position. So let us say this is the maximum compression. Now, based on this mean position, this distance is our a minus x naught number. Okay. So at this position, what is happening? So spring is being compressed by this much. So welcome my dear students. So in this lecture series, I am going to solve some of the interesting numerical problems from the book Pathfinder. So it is basically for the JEE Advanced preparation. So let us start the session. So there is a plank which is being pushed on a frictionless horizontal floor with a constant velocity of u equals to 1.5 meter per second. So there is another block which is gently placed on the plank and slides for a while, acquires the velocity of the plank and then moves together with the plank. That means there is a frictionless floor. On that floor, so there is a plank is resting and I am putting another block on that particular plank. When the plank is moving with a constant speed, that is equals to u is given as 1.5 meter per second. Now at that instant, you are putting this small block, let us say B, is put on the top of A, and A is the plank. Now it is said that they move together. And if the agency that pushing the plank has to do a work of 11.25 joule, that means in order to pull the plank, so I need some kind of external force. Let us say capital F is the force acting as the external force on the plank A, and because of that the plank is moving. Why? Because on the other surface, this surface is frictionless, mu is not equal to there. So mu is 0 over here. So there is no friction on the surface on which the A is in contact with the floor. Now since B is moving in with the same speed of 1.5 meter per second, that means in order to move the B, the friction is acting in this direction. Okay. So the friction is acting on the B in the forward direction. Similarly, the friction will act in the opposite direction for the A block. So ultimately, initially the block B is at rest. Okay. So you just drop the block B and ultimately it will act in a velocity of again 1.5 meter per second. Why? Because both of them should move with the same speed. So that means for the block B, can I say that block B is being pulled by a frictional force A, and corresponding to that, what is the acceleration of the block B? That should be equal to F by small m. And that small m you have to calculate the mass of the block. So corresponding to this acceleration, let us say after time t, the velocity developed on the block B is u. Okay, so what is u? U is that velocity. Okay, so from that, if I use equation v equals to u plus at, so initially u is 0, a is f by m into t, and that should be equals to 1.5. So from that, what I'm getting, that t number, that is equals to 1.5 m by f. So this is the time after which the block B will get the speed of 1.5 meter per second. And in that period of time, let us say s is the displacement of the plank A. So that should be equals to again ut plus half at square. Ut plus half at square. Now regarding this plank, it is given that the plank is moving at constant speed. Okay. So pushing the plank is moving at a constant speed. So what is the displacement of the plank then? So displacement of plank is basically equals to u into t only. Why? Because a number is 0. So if I say u is how much? 1.5 into t is 1.5 m by f. That is the displacement. Okay. So corresponding to that, what is the work done by this force? So since capital F is balancing the small f, so can I say F equals to small f for the plank A? Now work done by capital A should be equals to capital F into displacement S of A, and that is equal to small f into 1.5 into 1.5 into m by f. Okay, that means f will cancel out, so I am getting 1.5 whole square into m. That is the work done by the capital F. So that work done is given as 11.25. That work done is given as 11.25. So from that, what you can calculate, that m number should be equal to 11.25 here by 1.5 whole square. And 1.5 whole square means 2.25. 2.25. And the numerator is 11.25. So ultimately what I am getting, that answer is 5 kg. Okay. So this should be the mass of the block B that I am placing over block A. Okay. So in this problem, what you have to do? The key point is the work done is given. So you have to equate that work done. And again, so plank is moving. It is given that the plank is moving with a constant velocity. So that means in equilibrium situation, capital H should balance the small a. Okay, that means in this situation, what I am taking the acceleration of the block that is equal to 0. Acceleration of capital A should be equal to 0. Okay. So moving on to the next situation. So in this situation, there is a ball of mass small m is suspended in a box of mass capital M. So this is the box of mass capital M and there is a ball of mass small m. Now what is happening? Now it is given that there is a spring of K and setup is placed on a horizontal floor as shown in the figure. With what maximum amplitude can the ball oscillate up and down so that the box remains standstill? That means let us say initially this is the natural length. Initially this is the natural length. So once we put the small m, so the block is trying to pull the string by this much distance. So let us say this is x naught number. Now what is the x naught number? At equilibrium condition, x naught should balance mg divided by k number. Okay, so this is the x naught position. That means let us say this is the position which is known to be as the our mean position. Now across this mean position, the particle is oscillating. Sorry. Across the mean position, the particle is oscillating. Let us say the amplitude of oscillation is a to a minus a plus a to minus a. So this is the amplitude of oscillation. So ball is performing the amplitude of oscillation of plus a to minus a. So when the ball is going in the upward direction from the mean position toward the negative extreme position, so can I say that from the natural length, this is the amount of compression of the spring? Now what is that compression? That is equals to a minus x naught. Okay. So during the upward movement of the ball is compressing the spring by a distance of a plus x naught. And during the downward movement, the ball is compressing or elongating the spring by a distance of again this much distance, because always elongation and shortening has to be calculated based on the mean position. So mean position, from that mean position, this is the final elongation and this is the final shortening. Now once the ball is moving upward, let us say at that situation, the spring is maximum compressed by this position. So let us say this is the maximum compression. Now based on this mini position, this distance is our a minus x naught number. Okay. So at this position, what is happening? So spring is being compressed by this much length. So corresponding to the at the point where the spring is touching the box capital M, so it is being pulled by a force of k times a minus x naught. Now if this force is exactly matching the capital mg force, then only I can say the box will remain standstill. So our condition is that in order to box to be standstill, that k times a minus x naught number must be less than mg. Okay. So from that I can get the expression for the amplitude value. So that is Ka. So Ka minus a into k into x naught means small mg. That should be less than capital mg, or a number should be less than small m plus capital M into g by k number. So that will be your answer. Okay. So during the upward movement, the spring is being compressed, and because of that compression only, there is a chance that the box may rise above the floor. Okay, so you are asked to calculate that condition, so that this force should be less than the mg number. Okay. Now moving on to the next situation. So there is a boy who is holding one end of an inextensible cord supporting a block of mass small m. Okay, at its lower end. So from this block, another block of mass capital M is suspended with the help of a light spring of stiffness K. That means initially the arrangement is like this way. Small m is there and there is spring fitted with that and there is a capital M. So once I put this capital M with that small m, so initially let us say the natural length is this position. Natural length is this position. So block will come down by this much distance. Let us say is x1 length that is equal to how much? Capital mg by k. Okay. Now there is a table. Now there is a table. Inside the table, you are trying to raise the or trying to rest the capital M. So let us say at that instant of time, this distance is x2. Okay, this distance is x2. Now from the natural length position, so this is our equilibrium position, or I can say this is the mean position. The mean position. So from mean position, so this is our natural length. This is the natural length position. This is our x1 distance, and from that mean position, I am resting the capital M up to a distance of x2, so that the capital M will touch the ground or the table. Okay, so you are asked to calculate that how far will the upper block move. Upper block means small m will move before coming to an instantaneous rest for the first time. That means what is happening once you are dropping the small m toward the table, that means you are willing to touch the capital M with the table. That means now the spring is being compressed. Okay, so finally what is happening, the spring gains some kind of energy. So can I write gain in spring potential energy? Gain in spring potential energy, what is that number? That should be equal to half k times x2 square minus x1 square. Why? Because x2 is the measured length from the mean position and x1 is the measured length from the natural length. So x2 square minus x1 square will be the value of gaining spring potential energy. Similarly, that spring potential energy that has been gained, so finally what we can say, since all the blocks are at rest, so there is no change in kinetic energy, delta k is equals to 0. So simply I want to consider the gravitational energy. So potential energy of the spring is being increased, so loss in gravitational potential energy. Loss in gravitational potential energy. So in that situation, how much the block has to be lifted downward? So that is AM into G into x1 plus x2. That is the loss in gravitational potential energy. So that means these two numbers should be equal. So what I can write, AM into x1 plus x2 into G should be equal to half k into x2 square minus x1 square. And if I expand it, it should be x1 plus x2 into x2 minus x1. So from that x1 plus x2, x1 plus x2 cancels out. So I am left with x2 minus x1. This number should be equal to 2 times the small m by mg by k number. Okay, that is the x2 minus x1 answer. So once I get the value of x2 minus x1 and I already know the x1 number, so finally x2 should be how much? 2 times of small mg by k plus x1, that is capital mg by k. Okay, now you are asked to calculate the total displacement of the upper block. So what is the displacement of the upper block? The upper block is displaced by a distance of x1 plus x2 then. Okay, so your answer should be x1 plus x2. So I have already got the value of x2. You simply add that. So another capital M will come. So your answer will be 2 times of G by K, take common, that is small m plus capital. Okay, so that is the displacement of the upper block before coming to instantaneous rest. Okay, so in this situation, in that situation, there is no change in kinetic energy, only the change in potential energy is there. One potential energy, there is a spring that is being gained, and there is another loss of gravitational potential energy. Now moving into the next situation. So there is a block of mass m of 20 kg kept at a distance of r equals to 1 meter from the central axis of rotation of a round turntable. Now the table starts from rest and rotates with constant angular acceleration of alpha equals to 3 radian per second square. The friction coefficient of the block and the table is given as 0.5, and you are asked to calculate the time from the starting so that the block is just about to skip. Okay, so in this situation, what is happening? If I see the top view of the table, so this is the round table. Now the block is placed at the corner position over here. Let us say this is the M mass is placed. So on the block, so there are two types of forces because the table is rotating with an alpha acceleration. So on this block, there is a one tangential acceleration AP is there, another due to the radial acceleration, the acceleration in this direction, radial. So one force due to radial acceleration is basically M into AR. That is the centrifugal force that comes into the picture. So centrifugal force is in this direction That is m omega square into r. Okay. And due to tangential acceleration, there must be one particular force that is along that particular direction. It should be m into at. So these are the two forces acting on the particle. Resultant of these two forces should be the net force acting on that. So net force should be in this direction. Okay, net force should be in this direction. So this is the capital F net. Now opposite to that, the friction should act. So can I say the requirement of friction must be less than the limiting value of friction? Now what is the requirement of friction? That should be equal to capital F net. That means m into under root of, now what is 80? It equals to r alpha whole square plus omega square r whole square. That should be under the limiting situation. It should be equals to mu times n. N is what? M into g, mu into mg. Okay. So now, if I simplify this, so m will cancel out. So under root of r into alpha. What is alpha? Alpha is 3. So it is alpha to the power 4. Alpha to the power 4 plus omega is what? Omega is basically equals to alpha into t, because omega equals to omega naught plus alpha t. And since that this starts from rest, so this number is equals to 0. So omega naught equals to 0. So only we are getting the alpha t. So it is alpha t whole square into r, again another whole square. Okay, again another whole square. That should be equals to how much? That should be equals to what? Mu g. Because already I cancelled the m number. So if I square the both sides, now this is the net force that is balancing the mu mg number. So if I square both sides, so ultimately what I am getting, so m will cancel out. So here I am getting alpha square into r square plus omega to the power 4 into r square. That should be equals to mu g whole square. Okay. Now what is alpha? Alpha is 3 square, means 9. And r is 1. Plus what is omega? Omega equals to alpha into t. Omega equals to alpha into t. So alpha to the power 4 into t to the power 4. Omega equals to alpha to the power 4 into t to the power 4. Same to r square. That should be equal to mu g whole square. Okay. So mu g equals to how much? 0.5 into 10 whole square. That means 25. So 25 minus 9 means 16. So I am getting alpha to the power 4 into t to the power 4 equals to 16. So t to the power 4 becomes 2 by 3 whole to the power 4. That means I am getting t equals to 2 by 3. So after 2 by 3 seconds, the particle will slip. Okay. So that will answer 2 by 3. Option number B. Okay. So in this situation, you have to take care about both the tangential as well as the radial acceleration. Now moving on to the next situation. So there is a function given that y equals to fx. About that particular surface, the particle is rotating, and in a horizontal surface. In a horizontal surface, the particle is rotating. So it is seen that under defined value of x on the surface, the speed v required to perform a circular motion is same. And you are assumed to get there is no friction. So at any instant, if I say this is the position where the particle is performing the vertical circular motion, horizontal circular motion about the circle. So can I say that on this particular point, the radial force, that is centrifugal force, will be m into v square by x. What is x? X is the coordinate, this coordinate. Okay. And mg is acting downward. Mg is acting downward. Let us say at that point, normal on this surface, this is the normal. Okay. And if I draw the tangent at this point, let us say this is the theta angle subtended by the tangent. So if that is theta, then this angle is also theta. This is 90 minus theta. And this is theta. So it is becoming n cos theta. And this becomes n sin theta. Okay. So that means that equilibrium, n sin theta number should balance your m v square by x number. And n cos theta number should balance your mg number. So if I divide these two, so I am getting tan theta equals to our v square by gx. Now what is tan theta? Tan theta is basically slope. So that can be written as dy dx number. Okay. So what I can write that, so dy should be equals to v square by gx into dx. So if I integrate it, So ultimately left hand side give y, that should be equal to v square by g into ln x. Okay, so this is the equation of the path. This is the equation of the path. So you are asked to compare the value with v to the power a ln x by g. So you are asked to calculate the what is the a number. So a should be equals to what 2 then. Okay, a equals to 2 because I am comparing the exponent of velocity. So velocity is v to the power a given. So here I am getting v square, a becomes 2. Now moving on to the next situation, here there is a uniform rod is bent into a shape of a square. When the rod is hung in a horizontal peg, on a horizontal peg, it does not slip. What is the smallest coefficient of friction that can exist between the rod and the peg? Now in this situation, what happens? There is a square shaped rod and you are putting it over this peg. Okay, so let us redraw the diagram again. So let us say these are the two diagonal of the square. Okay, let us say these are the two diagonal. So this is one end point. So square is like this. Square is like this. Okay, this is the square which is hanging from the peg. So the point where the peg is supporting the wire is over here. So the component of weight that should act along this vertical line so that it remain horizontal. So this is our mg number. Okay. So at this position, n is acting over here. Let us say this angle is alpha. Let us say this angle is alpha. So now I can say clearly that if I concentrate on the triangle, let us say ABC triangle. ABC triangle. Okay. Now this angle is 45 degree. This angle is 45 degree. And what about this angle? This angle, let us say this x. Now regarding the x number, x is how much? X is basically equals to 180 minus 45 minus alpha. Okay, this is the x angle. Corresponding to that, let us say this is the y angle. Now what is the y angle? Y should be equals to 90 minus x. So 90 minus 180 plus 45 plus alpha. So that is 90 minus 180 is minus 90. Minus 90 plus 45 means minus 45. So it becomes alpha minus 45 degree. Okay, this is alpha minus 45. And what about this angle? This is 180 minus alpha. So now I can draw one triangle like this way, ABC triangle, whose all the three angles, let us redraw it. So this is the one triangle ABC, where this angle is 180 minus alpha. This angle is y angle, that is alpha minus 45. Okay, and this angle is 45. Okay, so now for this triangle, can I say the distance AC is the half of the diagonal? Now diagonal is b root 2. So that means AC is b by root 2 number. Okay, b by root 2 number. And this AB distance is given as a number. Okay, now apply the sine rule for this triangle. So can I write a by sine of alpha minus 45 should be equals to b by root 2 sine of 180 minus alpha. Now sine of 180 minus alpha is sine alpha. So I am getting b by root 2 sine alpha. And here I am getting a by sine a minus the formula. So if I take sine alpha minus cos alpha, whole divided by root 2. Okay, so this root 2 and that root 2 becomes 2. So 2a sine alpha should be equals to b sine alpha minus b cos alpha. Okay, so that means b times cos alpha, that should be equals to sine alpha into b minus 2a. So what I am getting, cot alpha, that number should be equal to b minus 2a by b. Okay, so or I can say 1 minus 2a by b. So that is the answer for the cot alpha. So now check for the equilibrium of the ring. So at the equilibrium position, so normal is there. So because of the normal, so component of mg that is coming in this direction is mg cos alpha. Mg cos alpha. And that should be prevented for sliding by the application of friction F. Okay. So F should be equals to mg cos alpha, and that should be less than our Fm number, limiting friction. Now what is limiting friction? That is mu into mg sin alpha. Okay. So can I write mg cos alpha should be equals to, under putting the limiting condition, mu mg into sin alpha. Okay. So from here I am getting mu equals to cot alpha. Okay. So answer for mu is cot alpha, and I have already calculated the answer for cot alpha. So cot alpha is how much? 1 minus 2a by g. So for this situation, the answer will be 1 minus 2a by b. That will be your answer. Okay. Hope you understand this.